Thanks a lot for the invitation and for the opportunity. First, a bit of personal history, then a bit of history in the field. Who remembers what this is? Okay, what is it? You don't know. Victor Schubscher said he doesn't know. It's IBM from the mid-90s who started the e-business wave, because IBM almost collapsed in the early 90s and then rebound and came back by inventing and pushing e-business. I got this from the official IBM history website, where they claim that they focused on this for the next decade. At the time, I was just joining IBM research. IBM was inventing e-business at the time, and the researchers at IBM were making it secure. And secure electronic commerce on the internet, that meant first and foremost that you could not be cheated by the potentially malicious merchant, and the merchant could not be cheated by you, the potentially malicious customer. So it is about a fair exchange, right? You have to pay, you want to pay on the internet only when you also get the goods, right? And this led to research at the time like optimistic fair exchange. Optimistic fair exchange is a secure protocol, but it requires a third party, because it's otherwise, if you're not optimistic, you need many rounds of interactions for a fair exchange. Then, if this is optimistic, it means that if one of the party cheats, you have to go to a trusted third party, and this trusted third party will resolve the exchange or the dispute, and this is a cryptographically sound version of doing this. And then there was just the question of how to actually implement this trusted third party in the real world. And that's when we started to look at distributing this trusted third party, right? And along came work, our first work joined with Victor also here and Klaus Gustavi on Byzantine agreement, because we wanted to make this trusted third party more secure. And that's how I started to do distributed protocols and consensus protocols. And remember, this was around 2000. Consensus protocols at the time already had a longer history. We had looked into what was available, what was done, what was actually state machine replication. This was not clear to us at the beginning. What is the difference between state machine replication and consensus? And so we realized, oh, there's a deep history. There has been theory research from the 80s onwards. Actually, also at IBM at the time, the 1980s papers, Dolev and Strong were also an IBM researchers. But there were lots of theory and no systems, and not even implementations or prototypes. Yeah, and then around 2000, there was a new generation of researchers. We were perhaps also part of this, approaching it from a practical viewpoint. The MIT, Liz Barbar-Liskov and Miguel Castro at MIT called it practical Byzantine fault tolerance. I was the first protocol taking these consensus ideas into a somewhat practical thing. They started to build a system, okay? They built a system that was actually a prototype system, an academic prototype system. And in the following decade, from 2000 to 2010, there was like a little arms race. Who can make their PBFD version a bit faster and so on. But there was no one interested in the actual system in practice, okay? And at the end of the decade, we had a workshop at the Distributed Computing Conference where researchers came together and were wondering why nobody actually was using the thing, okay? Because we had this great research and nobody was using it. And it was really depressing, yeah, because we said, who is going to use it? Has the moment for widespread deployment actually arrived or not? There was even Petr Kuznetsov, who is also still working on this demand. I said, hi. Wrote a summary of it later. Industrial software, it tends to ignore BFT-related research, and hence for the less consistent, crash-tolerant and simpler versions. And that was it, okay? And we were all depressed and said, gonna do something else, okay? Little did we know that at the same time, Satoshi had just mined the Genesis block, yeah? So the question in the audience.
That's exactly what I was going to ask.
Little did we know about Satoshi at the time.
Nobody mentioned Bitcoin at this paper. At this conference.
Nobody knew about Bitcoin. I think nobody knew about Kit, and this is what I'm going to say. Nobody in the research field knew about Bitcoin until maybe 5 years later, because from a cryptographic viewpoint, the cryptographers were more like, oh, there's a payment protocol, a secure payment protocol, but we can trace every single transaction, so it's trivial. They're not interested. And the distributed computing people did maybe not understand it, or maybe they would have said, it's not formulated in a way, why should it do consensus? It's probabilistic and synchronous, we know how to do this, yeah? So nobody was interested. However, the model became then viable with the cryptocurrencies, and the reason why this was not used before is just because it's a model, right? It's an assumption, and a security system does not make sense unless your customers, so in practice, a security system does not make sense unless your customers also believe in the assumptions that are underneath, that they also buy into your assumptions. And that's what the cryptocurrencies have done, make these assumptions viable for many people in practice. And to come around full circle, now we're working again on making electronic commerce more secure, but in a different way than it was envisaged at the past. And one could definitely also give a similar story about why the original digital cash schemes from Chaum in the 80s and 90s didn't make it, and now there are more elaborate ones. Okay, so today we are in full swing in more research, but also deployment in practice in consensus protocols. So in the rest of this talk, on the main body of this talk, I would like to go here through a list of models that I just discerned today, or I defined today, in which you can categorize the protocols that are used in today's blockchains. Yeah? It's not so much academic, but more from the field, from those models that are actually used. Going back to the motto that the models are more important than the actual protocols. And then I would like to focus on two models, the generalized trust model and also on the asymmetric trust model, and discuss those. Yeah. So threshold trust, symmetric threshold trust, is what is perhaps best known. This is the model like the academics started. They said, let there be n nodes and some number f of them are faulty. Yeah? And this is the model that we have used most exclusively for maybe 25 years or 20 years in consensus research, which is a good simplification of what one can do. But today there are other things. Yeah, there are certain issues with this model that have been found not to be the case in the cryptocurrency world, for example. So there are n nodes, and we say some number of f of them are faulty, and we need n bigger than 3f for the asynchronous protocols or for the partially synchronous protocols. We have textbooks. Here is my favorite textbook on the topic. So it's all very well established. And there are some chains that use this model, or actually have started to use this model when they were at the outset, largely they based their prototypes, or their actual deployment and practical softwares, their production softwares, on the existing literature. I would say Tendermint Cosmos is part of this, not that they just literally took it from the textbook, but they were definitely coming from the corresponding academic environment. Internet Computer or Hyperledger Fabric and some others are also following this model, where they're just simply votes. Yeah? This model has also been called proof of authority sometimes, because you have to assign these votes, and of course the system could replace the set of voters as it goes along, but it's clear who has, there's a global notion of who has the authority to vote here. There's a model that I would call generalized trust. It's a model when you are departing from the view that everybody has the same influence, and it's even more general than saying you have weighted votes. It's more general because you can say either 3 of those over here plus 1 of them, or 2 of them plus 5 from the 700 over here have the power to approve. Yeah? These models have been looked at under the topic of generalized quorum systems, for example. These models have been studied very deeply in secure multi-party computation, where one has shown that one can do secret sharing from it, and from models that are formulated in a particular way. I'm going to focus on this later, not yet here. In the simplest case, you could just have a monotone Boolean formula that enumerates your quorums, your power sets, or also describes the complement of your quorums, which would be the parts or the collusions you're trying to tolerate, which is called a fail-prone set then, and together they make up a fail-prone system. So in this case here, we have a heterogeneous model where not all nodes are the same. Some of them can be more important in certain combinations. It has been recognized all along that there is this concept of Byzantine quorum systems from the 90s also. Malky Ryder and Hirten Maurer formalized this under the notion of a Byzantine quorum system. Interestingly, this is not used by any cryptocurrency, not used by any consensus protocol, this type of model. Yes, question?
Well, I think Yehuda Lindel's company at Coinbase is now doing
Oh,
things like
Victor,
this.
yes, Victor says that Yehuda Coinbase uses it. And I was also at his talk the other day, so I'm going to mention exactly the access structure they're using in the second part. Okay, they're using for threshold cryptography, actually, not for a consensus protocol. It's used for a threshold cryptography. So this model is also playing into threshold cryptography, right? Yes, thank you for the comment. Yes?
Was this the model in Stellar too?
Is this the model in Stellar? No. The model in Stellar is not asymmetric. The model in Stellar is not symmetric, okay? It's asymmetric. The model in Stellar is asymmetric. The model in Stellar is you have your quorums and I have mine. And maybe you have consensus and
So
maybe not.
Symmetric means everybody has the same. Oh, okay.
This is asymmetric. This is, you see Stellar here as well. Stellar is listed here. Ripple actually started this. I'm going to focus on this also more later. Take a step back. This here is a quorum system, okay? It means, strictly speaking, that we all are prepared to tolerate certain nodes from failing, like the two red ones here, yeah? The special case of 2 being less than 7 by 3 divided by 3. In the Stellar world, in the asymmetric world, every participant now comes with their own such quorum system. I've only depicted 3 of them here instead of the 7 that I would have needed. Actually, I can also move things, I can show things here. There are only 3 rings here, but in principle, every one of the 7 participants would have to declare such an assumption on the trust on the others. It's representing a certain social trust. And it's also heterogeneous and it's also asymmetric, yeah? Ripple and Stellar started this, and I'm going to focus more on those in the second part of the talk. So I'm going to leave them for the moment, okay? And I'm going to go on towards other chains and towards other models that have been used by other chains. So there is a model where you are not asking a strict subset that is somehow derived from a majority or so for votes. Yeah? And this model, I would call it unstructured voting or probabilistic voting, where we are not getting votes and decisions with certainty, but only probabilistically. The Avalanche protocol is maybe the prime example today of this type of protocol. And we heard a talk yesterday also about this, so maybe I'm not going to say too much of this, except that these protocols, interestingly, they have come with a DAG most often. It seems to be not strictly required that you use a DAG for this type of protocols, but initially the Avalanche protocol used a DAG. The early I think it was called Phantom and Phantom DAG later from Sompolinsky and Zohar, and so they used similar ideas. Unstructured voting, probabilistic voting, asking some number of other nodes for their opinion and then switching to the other opinion and not getting the strict overlap guarantees of quorum systems. There has also been the IOTA Tangle, which is another DAG-based system that has been around, and there's also a chain. So these systems also have a long history. I think they are probably the least well understood today. They're not that prominent either compared to the, if you would take the market cap of the cryptocurrencies and divide them into the type of protocol assumptions here, then they're not among the most prominent ones. But they're definitely interesting for their features, for their technical features. You know, but I haven't mentioned it yet, that in the cryptocurrency world, we want to be permissionless, right? The protocols I have mentioned so far, they were permissioned in the sense that there had to be a global knowledge on a list of nodes ahead of time. This is certainly the case for the protocols that the researchers started with, the BFT protocols. So everybody has to know who can vote, yeah? And this type of assumption has not been very, let's say, favored in the cryptocurrency world, because you wanted to be able that everybody can participate in a protocol just like Bitcoin allowed. Yes, and that was a question.
So in this model, so the quorum is defined on the fly, that parties are participating, and then there will be at one point they'll do a random sampling, and then
in this case, I think there wouldn't be a quorum, but there needs to be a list from whom you can sample. There needs to be some kind of membership thing so that you know whom to talk to. And I think this is typically established by stake nowadays, yeah? by holding of cryptocurrency among validator nodes, and that will also bring me to my next types of families of assumptions. Yeah.
So in the previous case, it felt more like a mechanism. The original model is,
in the previous case, yeah, you're right by saying I'm not clearly distinguishing here between assumptions and protocol structures, and it's by choice, yeah. It's by choice because I wanted to get an overview or present to you an overview of how we could understand these protocols. And if you now say Avalanche protocol that uses some probabilistic voting thing has the same trust assumption and the same mechanism as, say, the actual Tendermint, which uses voting with stakes, it's both elements, right? I am going to focus now a bit more on stake. Stake is holding of cryptocurrency that makes you eligible to vote, okay? The more you hold, the more power you have to vote in a protocol. And this can be understood as a generalization of the threshold BFT model, at the same time also as a specific special case of the generalized model, right? Because here, 1 unit of stake is 1 unit of stake regardless of who this holds. So it's only a special case here. But nevertheless, you can understand many of the existing protocols here in this model, where we just vote based on stake, and we can use a lot of the type of BFT literature in this model. It still requires that the system follows the certain properties, or the protocols follow the properties of voting, because we have quorums, we have rounds, we need overlap of a certain majorities between two quorums, and so on. Yeah. A new element that can come in here is the so-called flashing. Yeah? This is when there is a demonstratable or provable misbehavior by a participant, we can take their coins away. And that's a new element. That's why it's not exactly the same as the voting from before, because there nobody was losing their vote. This was just abstracted away, was not part of the picture. So this is perhaps one of the most popular models that is used today. Certainly if you look at the new chains here, like Aptos, Sui, and so on. Yeah. But it's not only this, because the bigger chains are using different protocols, namely with randomization added, some of them. There is a model where you can have a pure randomization effort, which is like select a node at random according to their stake, with the idea in the back of your mind of the mining protocol from Bitcoin, that there is like a lottery that selects a node to write the next block with a certain probability, and you do this according to your stake holdings. And this is mainly the idea that comes with the cryptographic VRF that has been pioneered by Algorand. Even though I don't list Algorand here, I'm just going to say why. But I'm mentioning here Cardano and the Ouroboros protocols as, in my understanding, the purest representatives of this class of protocols. So you have a probabilistic choice. The actually most popular protocols nowadays are combining votes with probabilistic choices, yeah? In stake-based voting. So they would use randomization to select certain nodes. They would use also votes to approve certain random choices that have been made, as the Algorand protocol itself does, picking some nodes or maybe randomly electing some nodes into a committee, or the Ethereum protocol that came along with Ethereum 2, yeah? The one that also has now divided the protocol mechanism into like two components, one that is randomized and based and more responsible for the liveness, and the second component that is more using a quorum-based approach, using stake for voting, but that is slower. Yeah. So the what are they called? Ghost, LMD Ghost, and the Casper. But there is also Polkadot. This is something similar, and I will put Algorand here. It's probably the most one of the most popular protocols today. Then there is also other assumptions that people have started to make, namely, I can demonstrate my voting power, I can gain voting power by investing some resource other than work. Yeah? Work will come as the 9th model. Some resource like time, I have to wait long enough, or some resource like storage space. Yeah? So the storage-based protocols like Filecoin, they are using voting power based on how much storage you contribute to the network, and then give you corresponding power. Interestingly, there is always in these storage resource-based consensus protocols a time delay, a time component, so the verifiable delay functions, the VDFs, they play also an important role in these protocols. SHIA also has a combination of a VDF and some storage component. Yeah. So this is another interesting component, another interesting design where voting power is not gained by an on-chain resource, by a coin, but by some resource that you invest externally. And now, last but not least, but I guess you're all aware of it, there's the proof of work. That's the furthest away now in my line of models from the original voting-based protocol. That's maybe also why it was hardest to understand for the traditional protocol researchers what happens here, right? There is a resource like work, proof of work in the Bitcoin protocol being invested, and many coins, many cryptocurrencies have followed on this model where the resource by itself, the resource investment, is otherwise pointless, right? It's otherwise a waste of work instead of a proof of work. And I think nowadays the biggest investors of work for the Bitcoin chain are in the US and still in China, but the biggest mining farm here, I looked this up the other day, the biggest mining farm in the US has about 400 megawatts of installed power, and this is like one of the smaller nuclear reactors in Switzerland, yeah? And this is constantly running and burning electricity. So these are the 9 families of protocol assumptions that have been used that could be distinguished here. And if you know another one, yes, let me know.
It's a really great taxonomy. I guess I don't want to like nitpick it to death. I guess why is proof of work like all bucketed into one and then proof of space is separate? And there's a lot of different versions of proof of work that could be separated
You're
out.
saying
like,
why is proof of space
how did you
or proof
come
of
to this
storage
and
is
decide-
different from proof of work?
How did you decide 9 was enough and not like,
Yeah, that's a good
consensus
question.
7 or 11?
Okay, so why is proof of work not the same as proof of space or proof of delay? That's correct. That could be also organized a bit differently. On the other hand, I would not really want, I'm also looking at the protocol structures here, how the protocols are structured. What do you need to implement it? Which kind of techniques do you want to invest in for either going this way or that way? And then they're different, right? The protocols look quite different for the space and for the proof of work. Proof of work is really simple, right? But on the other hand, many people have recognized that it's also really wasteful. Huh?
I mean, I guess I would push back and say like Bitcoin proof of work Nakamoto consensus is simple, but most of them didn't go anywhere in industry, but there were all these other like hybrid proposals like Bitcoin NG and things like that, where you sort of do proof of work and then elect a committee.
Okay. Also, you're saying that the hybrids between proof of work and quorum-based protocols, I left them out. And that's true. And I think it has to do with what I wanted to do here on this line, usually showing the chains that actually use this model. And I'm not sure if this actually used. If you know a chain that somewhere has one of the larger market caps that actually uses Bitcoin NG or one of these protocols, I'll be very interested. But maybe the simplicity of the proof of work has made the pure proof of work here prevail, as opposed to the hybrid designs and so on, where you still have some elements of this, yeah. I mean, I also glossed over, for example, that in these DAG protocols like Phantom DAG or the Conflux, there needs to be a proof of work type thing as well, and IOTA tangle there happens as well, yeah. But it's the structure of the protocol that looks different at the end of the day, yeah. It's also that there are so many protocols, it's really hard to keep track of them, and this is just one attempt to keep track of them in a manageable enumeration, yeah. Okay. With that said, let us go forward, or in a sense backward, and go back to these protocols where we have votes, yeah, and quorum systems and votes, and that's it. The model of generalized trust is the model that is a first generalization of the original voting-based quorum system model. And it's based now, we have a technical audience here, so let me just jump in with a definition of a Byzantine quorum system. A Byzantine quorum system is this generalization of the threshold n bigger than 3f to arbitrary set systems, right? And it starts, so historically it starts in the work of Malky and Ryder, and concurrently with work by Hirt and Maurer, and here are the years of the corresponding journal publications. And there's definitely happening in these two different fields of cryptography, cryptography, multi-party computation research, and distributed computing research happened concurrently. So the idea, time was ripe for these ideas. You start with an adversary structure. Right? You start with specifying who we think could fail. Yeah, so we have a set system corresponding, or it's called a fail-prone system, and the system is prepared to tolerate any set of these Roman F parties failing together. Yeah, could be specified in arbitrary ways, and that makes it now interesting. How to actually specify them, right? What one can do from this is then derive a quorum system. The simplest thing is just to say the complement of every fail-prone set is a quorum, but it's not necessary, certainly not. In the cryptographic literature, when we talk about access control, it's much more often that we specify the quorums, like the access systems, like in a secret sharing context, which corresponding groups are qualified to recover the secret. So something here is a quorum when it's part of that set of quorums, which is called a quorum system, if any two quorums overlap in at least one more node than a fail-prone system, okay, a fail-prone set. So you take the overlap of two quorums, and you subtract any of those you're prepared to tolerate to fail, and you have to have one more node. This is the one where the consistency in the protocol will reside on. This is, as I said, symmetric trust, and here's a picture of a quorum system where we can think that we can tolerate some combinations of two parties to fail, namely among the XYZ parties, any two could fail, or among the PQR parties, any two could fail, but it's not possible that any of the two higher and lower subsets fail together, but it's possible that one of them fails, right, up to one. So these set systems are always closed on the subset. And so the fail-prone system is listed here, and the quorum system, the corresponding quorum system is this. Yeah. In this model, the nodes, they are trusted differently, but they have the same trust, yeah? So they trust all in the same way. So it's a common trust assumption that they have to be buying into, right? And it's not so clear anymore why you should use this or that trust assumption, but that's how it is, yeah? In this model here, with this model, there have been a lot of research results on distributed cryptography and also on consensus protocols. As I say here, it's well known in theory, but it's not really deployed, except for now comes the point with Coinbase. If you were at SBC, the Coinbase Vault, their key management system does a kind of a threshold crypto system where there's an access structure, that's a monotone Boolean expression that's listed down here, where there's an AND at the top level, and one of the three components here further subdivides into a threshold access structure. So you need one offline server, and you need the offline server, you need the human approvers in total, and you need the NPC servers, and there can be many NPC servers actually together. K could be there, and there's again a K out of K. So at the top level, this is a 3 out of 3, but the human approvers, they're going to be anything like 2 out of 20, or even a more generalized access structure. So this is an example of a generalized access structure in practice. Is it used for other things in practice? It's not clear. It's definitely possible to take the existing protocols and run them in this model. A lot of them, also a lot of threshold cryptography, but it's not necessarily the case. I wanted to focus for a short time on a typical protocol in this model, maybe for those who haven't seen this yet, and give you some background here of why Byzantine quorums make sense, right? And so it's just like a bit of taking a step back here for those who are not into concurrency literature. The very simplest thing that you can do with these quorums is implement a shared storage space that's in concurrency called a register. And it's not pointless for consensus, because at the core of every Paxos or PBFD or whatever modern Aptos Sui type of protocol, we have one of those registers that's in there. There have been papers about the Paxos register as well. So this register the main thing is concurrency. You have concurrently a reader and a writer that's going to access it. In the simplest case, there's only a single reader and a single writer. And what has to happen is, but it's not implemented as a, it's of course implemented in the distributed system, right? It could be implemented with a generalized quorum system here. And so we have an event that when an operation starts, the model is asynchronous, the operation takes some time, and after a moment it terminates and completes. And now what does it mean for two operations to be concurrent? Well, it's when the first operation ends only after another operation has started, right? If an operation starts, there's a picture here, of course, yeah. Now I can even draw it, okay? So if there is an invocation operation here and a completion operation of this operation O, there's an operation O prime, and the operation O prime is invoked before operation O completes, then these two operations are concurrent, right? And otherwise, they are preceding. So the question, of course, is how should this register behave when you access it concurrently from one client or for maybe multiple clients? And so there is this canonical taxonomy that also goes again back to Lampert. And now, how many of you have in the audience here have seen this before? Oh, not even too many, okay? Not even a majority. Okay, so primarily you want this storage thing to be safe, right? You want that if a operation like that, there's a first blue writing operation here that writes the X, and then there's an operation like the one down here that reads and is not concurrent with the write operation. You want to read, sorry, this is the wrong one. You want to read the value that has been written there before, okay? So that would be an operation that starts here that must return the X because it's the X that has been written here in the very first operation. The really interesting question comes up when you look at concurrent operations, like a read concurrent with a write. Yeah? So this orange read operation here is a read that already returns the value that is being written concurrently, the X. Yeah? And this is definitely possible in implementations or something. It's just a specification. We call this a regular register if it does that. It's also an atomic register that had this feature. This could happen. An atomic register now is something you can imagine again easily, namely as in a register where the value from the point of view of the observers has to change at an atomic point, at a single point in this logical time. The regular register, the orange, well, the one that's depicted in orange here, but also later, is a register that may return the value that was written there before or the value that is being concurrently written, right? If some nodes are already in the process of upgrading it, it might return the new value. So the orange read operation here, the first returns the value that has been written there before, and the second one returns the value that is being written now. The red one is concurrent to this orange read, and it returns the value that is being written, also the Y that is being written here in the second part. So this type of concurrency, this is what it is all about. The atomic register here, so for the atomic register here in the purple read, you have to ask then that it actually returns the Y, because the register has the node R2 here has already observed the new value, so it cannot go flip back in time. If you're looking at only the regular semantics, it might also return the value Y that was written there before, so you can have a flip forward and backward. How to implement this? Well, this is the topic of consensus protocols and well, it's at the core of all those consensus protocols. And in the Byzantine model, with the Byzantine quorum system, we do it like this. We have a writer with a logical timestamp. It's a single writer, makes things easy, with a digital signature scheme. And whenever it's implemented in a set of nodes that form this quorum system, the writer writes to a quorum of nodes and gets an acknowledgement from the quorum of nodes that they have stored it, okay, and then terminates the write operation. The reader will do something similar. It will ask all of these nodes for their current value. It will get values not from all, because some actually might be faulty, just like the writer may get values not from all the nodes, and will actually then go and validate the digital signature on the writer in this value, and take the value that comes with the highest timestamp, right? And it's possible to show an execution where we also flip back in time, just because the message from the writer did not arrive at the reader, and it did not arrive before the reader got his value. In this case here, the read-write operation would already have been recognized at this first node here. We'll get back the new value, would output this, but it would be equally possible that the two dots, the two events, the local events at the first process are swapped in the order. And in this case, you would realize that the blue reader would output the value x that was written, had been written there before, and not the new value. So this is at the core of those consensus protocols. And I'm showing the example here, of course, with the threshold quorum with 4 nodes and one of them faulty. But we can generalize this to arbitrary quorums, as I just said. Yeah.
I'm wondering, so you know, it's obviously a pretty general definition quorum system. So I'm wondering, what is beyond like weighted voting, what do you think is the most important thing that's
What
captured?
is the most important generalized quorum beyond weighted voting? You mean important in practice? Maybe the one that Coinbase uses for their thing, but they're not using consensus. It's maybe not a coincidence that this model is not used in practice, because it could be difficult to agree ahead of time, a priori, on who is how much trusted, right? It's certainly the case that many systems have some kind of exit, there is a super key built in sometimes, or somebody has like a backdoor into something. So there is a very special case of such a system running. But for a more generic type of cryptocurrency system, I haven't seen it used. Yeah, it has to do with a qualitative difference between the nodes that has to be discernible, and I have to be all agreeing on it. Yeah.
And I guess a related question is, how often is like the protocol you would write down for just unweighted voting extend easily to arbitrary quorum systems?
In this case here, the protocol is exactly the same.
Okay. And is that typical, or you usually have to work hard to get arbitrary?
In this case, the protocols are exactly the same so the protocols for the generalized quorums are exactly the same as the protocols for the threshold quorums, right? If we go to threshold cryptography, and that's more interesting now, then we have to use different types, but we can also do it. Yeah, threshold cryptography has been also very used a lot in quorum-like systems also. But then we need to upgrade the threshold crypto. Yeah, but it's largely known how to do this. Yeah, we have some research work on actually doing it, because nobody has done it in the industry, on actually doing it and measuring performance, and it turns out it's comparable, right? We're not losing much, because it essentially has to do with the complexity of specifying your quorums or your fail-prone systems, your adversary sets. If you can specify this if you do specify those in a Boolean formula, that can have arbitrary, like exponential complexity in the number of nodes that you're dealing with, then the protocols also have corresponding complexity. If you can capture this in what's called a monotone span program, do I have this MSP here? This is a linear algebraic expression of computation, where you look at the subspace that is spanned by the vectors held by the nodes. If you can do this, then you're efficient in polynomial time. And so I think it's very interesting, and it's overlooked. It's too much overlooked, this model, at the moment. Yeah. Yeah, as I said, we can do this. Just want to say we can do verifiable secret sharing, threshold crypto, threshold signatures in this model as well. But practice has not been buying into it. Maybe it takes another 20 years. We don't know. Yeah, we don't know about trust assumptions. Okay, then I want to go forward to asymmetric trust. But now one more question about the generalized trust.
I see occasional papers that say that the generalized access structures, secret sharing and generalized access structures are still exponential. The secret share size are still exponential. There are one or two.
So you're saying that papers claim that secret shares sizes are exponential. It's true, but it's actually a research topic, but it's much more in theory. It depends on the complexity of the access structure you're writing down in the first place.
And how is this different? Like, why are you getting so much efficient?
Oh, because we were restricting ourselves to the class of access structures that can be captured in a small number of, like in a config file with a small expression. This is not for all types of access structures, for all type of Boolean formula, because then we have too much complexity. Yeah.
So this is like restricted class of monotone span.
Sorry, no, the span programs are general. So the span programs are always, if you can formulate your access structure as a span program, then you have an efficient polynomial representation, size representation. If you are giving your access structure as an enumeration of set system, it's going to have exponential, it may have in the general case exponential size. And in this case, there is also exponential size crypto or consensus protocols, because you have to go and count. In the model with asymmetric trust, and I'm relying a lot here on the corresponding generalized trust, because it seems to be, well, it is actually the case that this asymmetric trust makes only sense when nodes have this power to describe heterogeneous trust sets. Yeah. So why are we interested in the asymmetric trust? And some of you have seen this before. Well, it's about taste, right? The Romans said you cannot argue about taste. Yeah. Either you like it or you don't like something. Yeah. And it's about trust maybe as well. Either you like an assumption or you trust that entity to do the right thing, or you don't trust that entity to do the right thing. Yeah? So it's a representation also of a certain social phenomenon, right? It's about assumptions, okay? It's about assumptions where if you do research in computer security, there is very often a security assumption, and then in the research world, people argue for a very long time about the validity of the assumption in the first place, because they cannot agree on whether this assumption is viable or not. In practice, there are going to be different assumptions, right? From an assumption, there will then follow a mechanism. And if we want to build a blockchain protocol from such personal assumptions, then we are in the realm of these asymmetric quorum systems with asymmetric trust. And it's also that the idea that came up first in the Ripple system, where Ripple system was designed to let you specify who you trust, to give you back a little bit of this permissionless element that was in Bitcoin. Yeah? And Stellar came later as a elaboration in some sense on Bitcoin. I have this listed here. So Ripple is actually old. Yeah? Ripple started something like more than 10 years ago. And they have a, I would call, homegrown consensus protocol that was inspired by quorum protocols. And we looked at this in a paper here in 21, and that was actually the first formal specification in type of pseudocode that we have for this protocol. But it's not a quorum protocol that we can derive from the textbook, right? It's rather the opposite. We see some issues pretty soon when we go into these protocols. It needs to be synchronous and so on. So it's not a type of protocol that you could find or even derive from the textbook. Knowing the textbook helps you to understand what perhaps should go on there, right? In the Ripple system, you define the set of nodes from whom you listen, from whom you receive votes. So this is called this UNL, a node list, unique node list. And you're only counting votes if they come from nodes on this UNL. Some of them could be faulty still, right? And some of them in your list could also be faulty. Hopefully we have enough overlap between our lists so that we have a quorum or we have consistency. Today, the XRP Foundation publishes such a list, and there are 35 nodes on it. And these 35 nodes are just, I would say, downloaded automatically by every client. And so we don't have this asymmetric trust. Everybody has the same set of quorums in that system. It means also that perhaps we could use a different protocol in that system, but the system uses that protocol for now. Stellar came as a fork of Ripple initially. And then they worked with David Maziere to develop what's called federated Byzantine quorums, which is an elaboration and a more complex and a more structured version of the same idea, where every node now has a local access structure, I would say, where they define whom they trust how. And here's an example. Now going back here, this to answer Tim's question from earlier. The example here is a config specification in the config file of one of the Stellar Development Foundation nodes. You have 8 nodes here, and you need 6 out of these 8 to agree. And among the lines here in the second level of the hierarchy, you need always like a simple majority, right? This is a Byzantine quorum system. It doesn't look like a Byzantine quorum in the sense you need a 2/3 majority, because there are like simple majorities on the lower layers here. And largely looking at this and trying to understand what goes on is what motivated our research on asymmetric quorums. Because the protocols also that are running are different. The protocols that are running in Stellar are different from the ones that run in that we find in the textbook. But this is the best example we have of a generalized access structure. If we have a config file like this, then you can compile this into efficient threshold crypto. So the monotone span program, and this is what we have done in our work also, is takes inputs like this, okay? Then you can do threshold crypto. Asymmetric trust. Every node now specifies its own generalized quorum system, okay? And here, and it does that also again through a fail-prone system specification. I say, I don't trust these two together, and I trust these more. In the picture here, we have the blue node and its view of the world among the 6. The blue node says its immediate neighbors, maybe one of them could conspire against me, or the people who are living across the street here, these X, Y, and Z nodes, maybe 2 of them are conspiring against me, right? So this is going to define our fail-prone system. And with a fail-prone system like this, so Q or R or X, Y or X, Z could, and so on, could conspire against this blue node. And from this, it's the quorum system of node P. We could now in this example say that we go around the circle and rotate in the circle. Everybody has the same view of this system here. This would be an asymmetric quorum system, okay? This would be an asymmetric quorum system. It's an example. Nodes, they are not only trusted differently passively, but they also actively express different trust assumptions. This is capturing the same idea as in the Stellar protocol. And if I go back here, then we can actually, maybe not going to run in the full glory through this, but we can actually specify this here as well, in the formal sense of a Byzantine quorum system by taking the former specification and extending it such that we have a quorum system for PI, a quorum system for PJ, for another process. And it has to be the case that a quorum for I and a quorum for J has an overlap even if we remove any fail-prone set that either I or J is prepared to tolerate, okay? So together they have always somebody who is correct in their both views. And for liveness, for availability, we can concentrate on a single node only. Namely, for each one of my quorums, so for each one of my fail-prone sets, for the nodes that can fail in my view, for each one of those sets, there has to be a quorum available that is not intersecting with them. And actually, the model is coming from multi-party computation even more. That was first formulated by Damgaard, Nielsen, Fitzi, and Desmet in an older paper, but it was immediately forgotten again, this 2007 paper. Now we can do, I have mentioned this here. There is a property where you can decide from looking at a asymmetric or a symmetric or a threshold quorum system whether or not this fail-prone pattern can even be tolerated. Yeah, this is why we said n bigger than 3f. In the threshold, it has to be the case that n is bigger than 3f for certain things. To actually guarantee the existence of the protocols or the threshold quorum system. For the generalized quorum system, we have to be able to say so. Generalized quorum systems exist if and only if no 3 fail-prone sets cover the space of all participants. Yeah? This is what has been called the Q3 property. It was one of the slides, but I didn't have time to go into. And a further generalization of this is the so-called B3 property, where we look at a fail-prone set of yours, a fail-prone set of yours, the other party, a fail-prone set of both of yours, and none of these combinations of fail-prone sets must cover the whole space. Then we have an asymmetric Byzantine quorum system. None of these 3 sets in any combination, if none of those are all participants, then you actually have an asymmetric Byzantine quorum system. The whole goal of this approach here is to actually run roughly or ideally the same protocols that we have in the threshold model, right? Why should we invent another consensus protocol for this model if the security assumption is generalized from the other model? And this is roughly also what one can do. Before I list the protocols, I want to give you one more detail on this, namely the execution model. In the execution model, there are going to be nodes that are correct, like before, okay? And there are some nodes in an actual execution. Some nodes are faulty, corrupted by the adversary. And in the threshold model, a node is either correct and benefits from all the guarantees of the system, or the node is faulty and we don't care. In this model here, we have nodes that are correct and made the right assumptions, and we have nodes that are correct and they just have the wrong assumptions. Yeah. So there are nodes about which we care, and we can still, well, let's say we're going to call them naive, and we care about them in a protocol because they play a more bigger role. In the traditional world, we say, what happens if f+1 nodes are actually corrupted? Well, then we just stop it, right? We normally don't look at the situation in assessing a protocol. What happens if too many nodes are corrupted? Because we cannot say much about it. Actually, we could, but we don't, right? Because there may still be this 1 or 2 correct nodes, but they're not getting consensus anymore. In this picture here, we have the naive nodes. There are a new class of nodes that come in that are correct, but have made the wrong assumptions, yet the protocol still runs because it continues giving guarantees to the wise parties. The wise parties are those who have made the correct assumptions. The guarantees are given for the wise parties only. Now, naive, we cannot give guarantees. And moreover, it looks like for many protocols we need a so-called guild, which is a set of the wise parties that is closed, that has a quorum inside for each wise party, and they're going to be the ones that provide liveness in the protocol. This is the picture here to show that we can take an existing protocols and replace only the blue parts in the protocol where we listen for a Byzantine quorum with the parts where the reader and the writer listen for their own quorum, a reader quorum and a writer quorum, just like in the read-write example we had before. And they're going to be consistent and live if both of them are wise. And we can do protocols like this, register emulations, the normal, the type of simple Byzantine broadcast, randomized consensus, and other things. And it's actually a very active area of research. There are other approaches that matter here, like the flexible consensus, which is a slightly different model, where the nodes adhere to an ordinary threshold quorum system, but the clients have an asymmetric subjective view, or the heterogeneous Paxos work that is also breaking up the symmetric and generalized trust assumptions. And that lets me conclude now. Yeah, Byzantine consensus protocols are here to stay. Assumptions are more important than protocols. These fields like generalized trust assumptions and asymmetric trust assumptions, I think they're important and relevant.
So for the asymmetric case, so I'm sort of struggling. Like, I feel like there's two competing forces. Like, one, you want to give people flexibility to specify their own assumptions and what they believe. On the other hand, you do need, for guarantees, you need at least implicit coordination between people's trust assumptions. So, like, how should I think about that? Like, what, like, why? In other words, if people are doing their own thing, why would those conditions hold?
Yeah, there needs to be correlation between people's trust assumptions, even though they should be individual, right? I think it's perhaps a way that we see in the live stellar network how they specify their things to what it could lead. So let me give you an example. It could be that we have a hierarchy, and at the top level, we have a couple of banks right now. Maybe we have a couple of trust providers for cryptocurrencies, and they are sure to have among each other their quorum consistencies, but they don't want to listen to their clients that they actually cater and serve business to. But I, as a client, I'm declaring a main bank and a second bank. It's not going to be a bank, okay? A main node and a secondary node that I trust, but I may not want to trust all these others out there that I've never heard of, yeah? So it naturally leads to some sort of hierarchy to manage the mental complexity of specifying such a model. I think this is a way of looking at what could happen in practice. It's clear that from the protocol themselves, if there is not enough correlation between the trust assumptions, then there's no consensus, and then they just fork, right? But it's actually giving back the element here of it's giving back to the quorum-based protocols the elements from the Bitcoin type protocols that if you just want to be live much more than safe, right? You can reduce your trust assumption a bit, right? And you can be live with your friends. It just doesn't matter anymore with respect to the rest of the system, yeah. And so it could naturally lead, in a sense, naturally lead to forks, yeah, in the space. But we haven't thought, nobody has really thought about joining these forks again later. But it's a social thing. It has to be connected with social processes. I think otherwise it doesn't work. Yeah. It needs to go through some social trust structures. Maybe we can use these protocols to actually understand what goes on in different contexts.
Can we go back to the definition of consistency in the asymmetric case?
Oh, the definition of consistency in the asymmetric quorum system. Right. Okay. Yes.
Yeah, I have two questions. First of all, should I think of this definition in terms of wise or naive nodes, like the PI and the PJ
Here,
nodes?
okay, should we think of this as wise or naive? There is no such notion yet, because this is the abstract specification of your quorum system when you set up the system before you are in an execution where some nodes are going to be faulty and some are going to be crashed. Only when you have an understanding of who is faulty, you can say who is naive and who is wise.
Isn't the set F supposed to specify
It ranges over all possible. It ranges over all possibilities, right? But it only ranges over those possibilities that the protocol or the nodes here have foreseen, right? Because it could be the case that one of my F, so that the actual F in the execution is bigger than this F set that I, as Fi, am prepared to tolerate. In this case, I'm going to be naive. Do you have the second question?
Yes. The second question is, why should I have the intersection there of the quorums of nodes I and j instead of the union of those?
Here.
Yes.
Because you are going to listen to a quorum of yours. I'm going to listen to a quorum of mine. Okay? And this still has to have, at least this intersection has to have one node in there that you think is correct and I think is correct. Namely, this.
Then it will be union. That's what my question is.
Yes, exactly.
Here the union, or
Fi star union Fj star, that the intersection of our accepting quorums have at least one node that both of us trust. So it's not equal to the union of values that we don't
okay.
trust.
Maybe there's a typo. I mean, let's discuss afterwards, okay? Yeah.
You're saying for the Fs, it should be the union.
Yes.
So the star is all subsets. The star notation, right? I didn't say this.
It's not a singleton. It's not a single set.
This the Fi star here.
Oh, okay. I think there's
So
something
this is
more happening
Fi
here.
star is a set of nodes. Fi star is a set of sets of nodes that
I see. Okay.
it contains all the ones that PI is prepared to tolerate, right? It's actually closed under subset.
I see. I think there is second level, which I'm not visualizing.
Yes.
Wait, isn't it the ones that you're not prepared to tolerate? Because it's the
No. The Fs are the ones that you are thinking could fail. It's a fail-prone. F is a fail-prone system, so it consists of so-called fail-prone sets, and every element in the fail-prone set is a set of nodes. So you think all of them together might conspire against me. Yeah. For example, any set of 2. Yeah, out of 7. That's the simplest example.
I need to parse this a bit
Good.
more.
I guess, yeah. I guess we have time for more discussions also later. But otherwise, yeah. Thank you again.